Okay, in this video we'll talk about the Butterworth filter, which is another filtering technique. We've talked about some filtering techniques before. For example, the moving average smoother is a type of a filter. We've talked about differencing. Differencing is a type of a filter, a very popular one with economists. That's a high pass filter, and the problem with it though is that yes, it does focus on the high frequency behavior. It does a decent job of preserving that, but it just doesn't do a very good job of eliminating all of the low frequency behavior. So it's the differencing filter is a type of a high pass filter, but it's just not very good. The Butterworth is an improvement, and that's why it's very commonly used among scientists and engineers, and that's what we're going to talk about in this video. Now, we're going to talk about two different types. We're going to talk about the low pass filter and the high pass filter. A low pass filter is the goal is to keep the low frequency behavior and eliminate the high frequency behavior. So by a pass, what we're saying is it passes it through and it filters out the other. So a low pass filter keeps the low frequency behavior and filters out the high. We'll also look at a high pass filter, which does the opposite. It says I want to retain the high frequency behavior and filter out the low frequency behavior. And with that, we will go over to R and let's practice with some R software. Okay, here's the syntax. It's very straightforward. Butterworth.wge is the syntax, and then the arguments are the data set, the order. This order is a very similar thing to like the moving average smoother that required an order. Same type of thing here. Type just simply stands for us, we're only going to look at a high pass filter and a low pass filter. So we're going to say type equals H or type equals L. Then there'll be a cutoff value. That cutoff value is important. We'll see that in the example below. And then you get the option to plot it. So that is the syntax. Very easy, just a quick little line there, and it takes care of that for you. Now let's look at an example. What we're going to do in this example is generate an AR4. This is an old example. Example 4.5 is this very AR4. And if you'll recall, this is one we're using quite a bit in this chapter. It is one that has two different frequencies. Now I can't look at those four coefficients and say, oh, that's got two different frequencies. I have to do some other things like look at the data. A realization suggests it a little bit. We'll see that in a second. And then definitely a spectral density plot certainly reveals that it's got more than one frequency. So let's do that. There's the syntax for generating a realization for an AR4 with those phi coefficient values. Then we'll plot it. So let's do that really quickly. And we have this. So what do you see? Well, it looks like we see some pseudo-sinusoidal behavior for sure, right? They're not perfect sines, but they're definitely going to be categorized as pseudo-sinusoidal. Why is it not perfect? Well, I see some noise on here. There's a lot of wiggle, a lot of jaggedness about it, and that comes from the high frequency content most likely. So it's not surprising that this may have two frequencies to it. Now, I can't tell what those frequencies are, especially for the high. You could pretty easily calculate the low frequency by just taking the whole number of points, divide by the number of periods, or the number of cycles, and that would definitely give you that. But let's go ahead and look at the parsin function and run that. And what do we see? So this is a spectral density plot, and we see a spike at 0.05 and a spike at 0.45, which definitely reveal that, yes, this thing does have two different frequencies. I know you could look at this thing right here, this little hump and this little hump, but that's just what we call an artifact of the data. It's not real. It's just some noise, and we have to ignore that. So there we see that the data set that we have from this realization is a two frequency type data set. Now, it may be desirable for you to only care about, only want to focus on the low frequency component. Or maybe right the opposite. Maybe you would rather focus on the high frequency component. Well, we don't have anything so far in our arsenal, that is the differencing or MA smoother, that would filter it in that way. But this Butterworth is definitely something that's going to work for us. Here's how we'll do it. We'll first of all do a low pass filter. That's what we've got here. The low pass filter means that we want to do what? We want to keep the low frequency content, the low frequency component of the data. We want to filter out the high frequency. So what we're wanting is that pseudo-sinusoidal pattern, and it would probably be much smoother if we will filter out the high frequency component. So what's the syntax? Low equals Butterworth.wge, data set name is X, type equals L because this is a low pass filter, cutoff equals 0.25. Why is that? Well, we know that we've got 0.05 as the low frequency and 0.45 as the high frequency. So 0.25 sort of sits far enough from either of them to not get in the way. So that's why we do that, and we won't plot it in this command. So we'll say plot equals false. Let's run that. And then let's do plot it from the values -20 to 20 and see what that looks like. And what do we see? We definitely see that low frequency pseudo-sinusoidal behavior. We do not see any of the jagged jiggle that came from the high frequency piece. So that is an indication that this Butterworth filter did what it was supposed to do. Now let's let the parsin command, which plots the spectral density plot, let's let it confirm that. And what are we expecting to see? We're hoping to see a spike at the low frequency location, which would be 0.05. Let's run that, and sure enough, that's exactly what we see. We see a spike at 0.05. So far, we're impressed with the Butterworth filter. It has done what it is supposed to do. Now, let's do the opposite. Let's look at the high pass filter. Now remember, this is the thing that the difference filter did not do so well on because it didn't do a very good job of eliminating the low frequency. But do the same type of thing. The syntax is going to look nearly the same. All you get to do is say high equals Butterworth.wge, X, type equals H, not L, cutoff equals 0.25, plot equals false. So that's pretty much the same command. Let's plot that, and before we hit run, what are we expecting? We're expecting none of that pseudo-sinusoidal smooth sine curve stuff. We're expecting instead a bunch of high frequency noise, aren't we? And look what we get. We get exactly that. Again, this is evidence that the Butterworth filter is doing what it's supposed to do. Let's let the parsin command confirm that for us. What are we expecting here? We're expecting a spike where? At 0.45. Because we are hoping that this filter got rid of the low frequency piece, meaning that we hope there's no evidence of a spike at 0.05. Let's run it, and that's exactly what we get. We see this spike at 0.45. We see nothing back at 0.05. Hey, this Butterworth filter has done what it's supposed to do. It definitely beat the difference filter and is really effective at filtering out what it needs to filter out and keeping what it needs to keep. So impressive. That is the Butterworth filter. Good news about it, man, really easy to implement. Just simple command. It's a one-liner pretty much. So really neat. You would need to look at your data closely to see where to make that cutoff value. That's one thing you would need to do. And one other little warning is the fact that as we've seen in some other smoothing situations, smoothing methods, end effects are an issue. Remember the end effects for the MA smoother, for example, you just don't even have data on the ends of the data set. And for some other cases, maybe you have data, but it just looks weird. Same thing is true here for the Butterworth. End effects are an issue. But other than at the ends, you can trust that data that sits in the centrally located areas. But that's the Butterworth filter. I hope that was easy to follow. Pretty cool technique. Use it when you need to filter out certain types of frequencies.